Welcome to the deep dive. Today, we are tearing into a really fundamental question. Machine intelligence. What is it?
Yeah, how do we even figure out if a machine is intelligent?
Exactly. And, what are the building blocks and maybe the huge challenges involved in trying to create it?
We've been working with excerpts from a lecture that gives a great structured look at these core ideas. It kind of walks us through the history a bit.
From the early thinking right up to today's hurdles.
Right up to the practical stuff engineers hit today.
Okay, so our mission in this deep dive is to unpack those concepts for you. We want to go from the big, famous, almost philosophical tests.
Like the Turing test.
Yeah, all the way down to the nitty-gritty of data and algorithms so you get a much clearer picture of what's really going on, under the hood in AI.
And there's really only one place to start, isn't there? A genuine classic.
The Turing test. Let's dive in. Alan Turing's paper, Computing Machinery and Intelligence, it's just foundational. Feels like the starting gun for so much AI work.
It really does.
But what struck me right away from the source material we looked at is that Turing's core question wasn't actually, can machines think? Was it?
No, that's a really crucial distinction the lecture makes. It argues Turing largely assumed we could probably build intelligent machines eventually. His immediate practical question was more like, all right, if we can build them, how on earth do we actually measure or test that intelligence?
So it was less about philosophy, consciousness, all that.
Less about that, yeah.
And more like an engineering problem. Like, how do you benchmark this thing?
That's exactly the view presented here. The Turing test is framed as fundamentally an engineering test. Assume you can build it, okay, now you need a standard, a way to gauge its capability. That's the problem Turing was tackling head on.
Which is pretty insightful, actually.
Right.
And this paper, it didn't just propose a test, did it? The source points out he basically mapped out the landscape of almost all the major AI fields we still wrestle with today.
He really did. It's kind of amazing. He laid the groundwork. You can see the outline of modern AI research right there in that paper.
All right, so let's look at some of those areas Turing basically predicted.
Yeah.
Because they also highlight where the challenges still are for AI.
Okay. The lecture specifically calls out several key areas. First step, searching.
Okay, but not just like typing into Google.
No, not just that. Think about the implicit search your brain does, like recognizing a face, in a crowd. That's a super sophisticated search process, right? Based on a lifetime of acquired data.
And current AI struggles with that kind of search.
Yeah, the source notes that AI still finds it difficult, that intelligent search that's deeply tied into acquired knowledge, not just, fast pattern matching or lookup.
Okay, makes sense.
Yeah.
What else did he see coming?
Reasoning. That's another big one.
Yeah.
The lecture points out that reasoning in the flexible, human-like way, applying knowledge to new situations, drawing conclusions, that's still an area where AI, well, it doesn't really pass a robust Turing-style test yet.
You can give it rules, maybe, but applying them flexibly is the hard part.
Exactly. Then there's knowledge representation. This is absolutely critical for anything intelligent.
How you store what you know.
Yeah, how do you take all the information you acquire and represent it internally in a way that's both compact and actually useful?
Okay.
The source links this directly to ideas like abstraction and representation in deep learning.
Yeah.
It even points to dimensionality reduction, which we'll get to later, as a form of compact knowledge representation.
Like boiling down complicated stuff into the essentials.
Yes, exactly. Because no system, human or machine, has infinite memory or processing power, right?
Yeah.
You need to represent knowledge efficiently to be able to use it for search or reasoning.
Got it. What's next?
Next up, natural language processing, or NLP.
Oh yeah, that's huge now. Chatbots, voice assistants,
Yeah.
they're everywhere.
And totally essential for AI. The lecture really emphasizes that so much of human interaction and even our reasoning happens through language. You can't really claim human-level AI without strong NLP.
It underpins so much.
Search engines, document analysis, you name it.
And then something that feels really intuitive for us. Computer vision.
Right. People seem to grasp AI working with images pretty quickly. We are visual creatures. Something like 90% of the info we take in is visual.
So it's a natural fit for AI research.
Yeah, and as the source highlights, a lot of the major AI progress we've seen recently, like getting good at recognizing objects, has been in computer vision. Big successes there.
Okay, and finally, the big one, learning. Learning from data.
Right. But the source draws a really key contrast here. while deep learning, excels when you feed it massive data sets.
Like millions of images.
Exactly. Humans, on the other hand, are often capable of one-shot learning.
Meaning?
Show a child one picture of an elephant, maybe just one, and they often grasp the concept elephant. Current AI, generally, it just isn't capable of that kind of learning from a single example. Not yet.
Huh. So even our most powerful learning systems are fundamentally different from how we learn with just a little bit of information.
That gap, that difference in efficiency and generalization from scarce data, that's a major challenge highlighted by the source. All these areas, sketched out by Turing decades ago, are still central to AI research and engineering today.
Okay, but if that's how we're thinking about testing intelligence, what happens when someone challenges that whole idea?
Years later, right. This next bit from the lecture, it apparently really shook things up during what was actually a quiet period for AI, an AI winter.
Yes, philosopher John Searle and his Chinese room argument. It's interesting, the lecture frames it not really as an attack on AI, but more as a really crucial clarification. It came during a time when AI progress maybe wasn't meeting the hype.
And it forced people to think more deeply.
Exactly, to think about what understanding really means for a machine.
So tell us about this thought experiment, the Chinese room.
Okay, so imagine a room. Inside this room is a person, let's say they only speak English. They understand zero Chinese, no understanding of the language at all.
What they do have are two things. One, a giant, totally complete Chinese to English dictionary. And two, a massive book containing millions upon millions of incredibly detailed rules for manipulating Chinese symbols.
Rules like, if you see this symbol followed by that symbol, look them up, then find rule number 76B, and based on that, output this other symbol.
Precisely. Super complex procedures, all purely symbolic manipulation. Now, people outside the room slide pieces of paper under the door with Chinese text written on them. Questions, stories, whatever.
Okay.
The person inside, following only the rules in their rule book and looking things up in the dictionary, processes the input symbols and eventually slides a piece of paper back out.
And what's on the paper that comes out?
Flawless, grammatically perfect, meaningful English translations of the Chinese text. It works perfectly. The output is indistinguishable from that of a native Chinese speaker translating it.
Okay, so the system behaves perfectly. It gives the right answers. What's Searle's big point here? What's the catch?
He poses his central questions. First, does the person inside the room understand Chinese?
No. Clearly not. They're just shuffling symbols according to rule. They have no idea what the symbols mean.
Right. But here's the killer question. The one that, as the source puts it, completely put Searle on the map and really challenged the prevailing view at the time, especially of those early expert systems. His question is, does the room understand Chinese?
The room, meaning the whole system. The person, the books, the rules, the whole setup.
Exactly, the whole black box that takes Chinese input and spits out perfect English output. Does that system understand Chinese?
And Searle says.
Searle's argument is, no. The room still doesn't understand Chinese, despite producing perfect translations. And this was a direct challenge to the idea that simply following a complex enough set of rules like those early AI systems with millions of hard-coded facts and if-then rules constitutes true intelligence or actual understanding.
Ah, okay. So it draws a sharp line between simulating intelligent behavior just by following rules and actually having understanding or consciousness.
That's the core distinction the source highlights. It's the difference between hard-coding responses, no matter how complex, and genuine comprehension.
It connects back to those early expert systems, right? The ones that could beat chess grandmasters.
Exactly. They did it by basically looking up or calculating through millions of possibilities based on explicit rules programmers gave them. Was that true chess intelligence, or just incredibly fast, complex rule following? Searle's argument pushes on that.
This raises a huge point then. How do we even define what counts as intelligent AI behavior if just executing complex rules isn't necessarily enough?
Well, the lecture uses a great, really simple example to illustrate this whole idea, the game of tic-tac-toe. We want an AI to play tic-tac-toe intelligently.
Okay, simple game. Surely that's easy for AI.
It is easy, yeah. But how you make it play highlights this idea of intelligence. The source outlines 3 different versions, 3 ways to build a tic-tac-toe AI.
All right, version 1.
Version 1, the lookup table. You literally hard code the optimal move for every single possible board configuration.
Like a gigantic list. If the board looks exactly like this state, make this specific move.
Precisely that. For every single one of the, few thousand possible states in tic-tac-toe, the answer is predetermined. The AI just finds the current board state in its massive table and looks up the pre-calculated best move.
Okay.
Now, the source argues why this, specifically in the context of defining AI intelligence, is not considered intelligent. It's static, the table never changes. It's specific, it only works for tic-tac-toe. It's explicit, all the actions are just listed out, and it's really just very fast lookup.
It's called stupid from an AI perspective in the source, right?
Yes, explicitly stupid, even though it would win or draw every single time.
Stupid but effective.
And the lecture makes that point too. Yes, stupid engineering solutions can be incredibly useful, powerful even, think beta-based lookups. But it's not what we're trying to capture when we talk about AI intelligence in a more general adaptive sense.
Okay, so that's the stupid way. What's a slightly more intelligent approach, version 2?
Version 2 applies dynamic rules or strategy. So instead of listing every possible board state, you give the AI some general rules. Things like, try to get 2 X's in a row. Or if the opponent has 2 O's in a row, block them. Or maybe take the center square if it's open.
So it evaluates the current board and applies these rules.
Yeah, it applies these rules dynamically based on the current state.
Is that intelligent?
Well, the source is a bit less definitive here. It says, okay, it's more dynamic than the pure lookup table, but it's still based on a set of explicit rules you gave it. It's maybe getting closer, but still rule-based.
Okay, so what's the approach that is considered truly intelligent in this analogy? Version 3.
Version 3, yes. This is presented as the most generic and intelligent approach. It involves 3 key parts. First, you need to represent the state of the game properly.
More than just the X's and O's.
Yes. You understand the current board layout, sure, but also the rules of the game. What are the legal moves from this position? You understand the fundamental structure of tic-tac-toe.
Okay, understanding the underlying principles.
Exactly. Second, you use an evaluation function. This is really key. It's a function that can look at any possible state of the board, even ones it hasn't seen before, and dynamically assign it a value or score.
Like, how good is this position for me?
Yeah, how likely am I to win from this state? For tic-tac-toe, it might calculate the probability of winning. The point is, it's dynamic, it's general, it works for any state, and it's implicit the value comes from some kind of calculation or learned model, not just looking it up in a table.
It's learning to actually value situations.
You could say that. And third, if you can computationally afford it, you include look ahead. The AI predicts potential future board states that could result from its possible moves and maybe the opponent's likely responses.
Thinking ahead a few steps.
And it uses its evaluation function to score those predicted future states. This shows a deeper understanding of the game's dynamics over time, not just the current snapshot.
Wow. Okay, so version 3, understanding the state and rules. Having a dynamic way to evaluate any state's value. And maybe looking ahead, that's the dynamic, generic, implicit approach. That feels more like intelligence.
Yes, and it's the kind of approach that could potentially generalize to other simple games, not just tic-tac-toe. It's contrasted starkly with version 1, the static, specific, explicit lookup table, which is labeled stupid from an AI perspective.
It really highlights the difference, doesn't it, between systems that just perform actions based on explicit, pre-programmed instructions like the lookup table or maybe even the Chinese room.
And systems that seem to grasp the underlying problem structure and can dynamically evaluate situations, like version 3.
This connects directly to another core concept the lecture introduces, which is looking at AI as essentially function approximation.
This is a really powerful idea, yeah. It's looking at what a lot of AI actually does, is trying to figure out the relationship between inputs and outputs when we don't know the exact equation, approximating some unknown function.
What kind of unknown functions are we talking about?
Well, the lecture gives examples like trying to predict a stock market crash based on maybe 4,000 different economic indicators, or trying to predict someone's likelihood of developing cancer based on their health history, genetics, lifestyle factors, all sorts of things.
Things where nobody actually knows the precise mathematical formula that connects all those inputs to the final outcome.
Exactly. You can't just plug the numbers into a known formula and get the answer. The true function, if one even exists in a simple form, is incredibly complex and fundamentally unknown to us.
So what AI systems do is?
They learn an approximation of that true hidden function. They do it by looking at massive amounts of data where we do know the inputs and the corresponding outputs.
And this is what makes AI so valuable, right? It's not a limitation that it's just approximating.
Absolutely not. The source emphasizes this isn't a weakness, it's the difficult and incredibly valuable task AI performs. Approximating these unknown, high-dimensional, complex, often non-linear relationships is something that's way beyond human ability to model explicitly.
Simple historical methods did this too, right? Like linear regression.
Yeah, linear regression was doing this in a very simple, linear way. Neural networks, especially deep ones, are basically doing the same thing, but in vastly more complex, high-dimensional, non-linear ways. They're universal function approximators, in theory.
So AI is essentially using data to build a model, a sort of mathematical black box that behaves like the true function, even though it doesn't know the function itself.
Precisely. It learns the patterns, the correlations, the structure from the data. And that, of course, brings us to the absolute necessity and the huge challenges of the data itself.
Right. For this function approximation magic to work, AI needs data.
And often, especially for modern deep learning, it needs vast amounts of it, huge quantities.
And you need different kinds of data, don't you? It's not all the same.
Correct. You need training data. These are the examples the AI learns from, the input-output pairs it uses to build that approximate function to tune its parameters.
That's how it learns the patterns.
Yeah. Yes. And critically, you need testing data, completely separate data, stuff the AI has never, ever seen before, to evaluate how good that approximation actually is.
Because you don't know the true function.
Exactly. Since you don't know the real answer key, the only way to know if your AI learned something genuinely useful, and isn't just memorizing the training data, is to test it on new, unseen examples and see how well its learned function predicts the outcomes.
And getting enough truly representative testing data, especially for these giant models, that sounds like a real problem in itself.
It definitely is a huge challenge. And, this loops back to that provocative question the source raises again.
The tic-tac-toe thing.
Kind of, yeah. Are deep networks just incredibly huge, incredibly sophisticated lookup tables?
How does that apply to, say, image recognition?
Well, the source uses the example of adversarial attacks. You've probably heard about these.
Where you change an image just a tiny bit.
Yeah, tiny, almost invisible changes to an image like a picture of a cat can cause a state-of-the-art deep network to suddenly become extremely confident it's looking at something completely different.
Guacamole, I think I read that one.
Guacamole is a classic example. It's wild, right? And the source suggests this kind of behavior could be interpreted as evidence that maybe the network isn't learning true, robust, generalized concepts like catness. Instead, it might be operating more like it's memorizing or partitioning its input space into a vast, complex lookup map. A tiny alteration just bumps the input image to a slightly different point in that high-dimensional map.
Where the pre-memorized answer just happens to be guacamole.
Exactly. Because of some weird quirk in the memorized patterns learned during training, not because it genuinely perceived or reasoned that the slightly altered cat was guacamole.
So it's like super advanced pattern matching on a surface level, maybe, rather than deep conceptual understanding.
That's the concern the source raises, yeah. It behaves like hitting an unexpected weird entry in a giant lookup table when the input shifts just a tiny bit off the training data it memorized.
Okay, beyond that sort of fundamental question about what's really being learned, what are the more practical, common problems with the data itself that the source mentions?
Two big ones are highlighted really clearly. First, maybe the most obvious, simply not enough data.
Especially for deep learning.
Yes, deep learning models are notoriously data hungry. The source literally calls trying to train a complex deep network on only, say, 1,500 examples ridiculous. You just can't expect good generalization from that.
But what about tricks like data augmentation? Flipping images, rotating them, adding noise to artificially create more data.
Yeah, data augmentation is mentioned as a common technique, an artificial trick to inflate your dataset size. But the source kind of questions its universal applicability. It suggests that if you genuinely lack sufficient real data for your problem,
then maybe deep learning isn't the right tool for that job.
Maybe the problem or the application just isn't well suited for this type of data-hungry AI in the first place. Augmentation can help, but it's not magic if the core data isn't there.
Okay, so not enough data is problem one. What's the second major data problem?
It's kind of the opposite problem, in a way. Too much data, or more specifically, too many features describing each piece of data.
Features meaning attributes, like columns in a spreadsheet.
Exactly. If each data point has thousands of attributes, The source uses an example of maybe 5,000 facts about a car. Feeding all of that raw data directly into a complex model can be computationally crippling.
How crippling.
This source gives a hypothetical example where some calculation, maybe involving interactions between all features, could take something like 54 years to compute.
54 years. Okay, yeah, that's definitely too many features to just dump into a model.
Right. And besides the cost, not all those features are even valuable. Some might be irrelevant garbage. Some might be highly correlated, basically telling you the same information multiple times in slightly different ways. Some might just be random noise.
So finding the signal in the noise is hard.
Figuring out which features are the important, relevant ones is a hard problem in itself. The source makes a nice biological comparison here. Our brains do this constantly. The optic nerve, for instance, doesn't just dump raw pixel data into the visual cortex.
It preprocesses.
It performs significant preprocessing and dimensionality reduction before the information even gets to the main processing areas. It filters and compresses.
Okay, so preparing and simplifying the data before you feed it to the main AI model can be a really crucial, maybe even essential step.
Absolutely. Sometimes making the learning task feasible and effective for the AI is more about smart data handling upfront than just picking a fancier algorithm.
And this leads us to a fundamental technique mentioned specifically in the source for tackling that too many features problem. Principal component analysis, PCA.
PCA, yeah. It's described as a really core dimensionality reduction technique.
Dimensionality reduction meaning reducing the number of features.
Exactly. The source calls it often the very beginning of the machine learning pipeline, a crucial step you often take to prepare your data for the actual AI learning part.
Like sorting and prepping your ingredients properly before you start cooking the main dish.
That's a great analogy. The goal is to clean up, compact, and generally make your data much easier and more effective to work with by reducing the number of features or dimensions. Think about that car example, maybe reducing 5,000 features down to, say, the 20 most meaningful underlying factors that explain most of the variation in cars.
Okay, and what does PCA look for in the data? What makes good data from its perspective?
Well, it aims to transform the data so that the resulting features have two main desirable characteristics. First, ideally no correlation between the new features. They should be independent, representing different aspects of the data.
So you're not measuring the same thing twice.
Right. And second, the new features should have high variance. Variance just means the data changes or varies along that feature's direction. Features that are constant or nearly constant across all your data points don't really tell your AI anything useful for making distinctions or predictions.
You want features that capture the differences in the data.
Exactly. High variance often means high information content.
So how does PCA actually find these magical new features that are uncorrelated and capture the most variance?
Okay, so without getting too deep into the linear algebra, PCA basically finds the average point, the center of your data cloud in high-dimensional space.
Okay.
Then it looks for a new direction, a new axis going through that center point, such that if you projected all your original data points onto this new line, they would be spread out as much as possible. That spread is the variance.
So it finds the direction of maximum spread.
Yes, that's the first principal component. It captures the single biggest chunk of variance in the data. Then PCA looks for a second direction, also through the center, that is completely uncorrelated, mathematically orthogonal to the first one, and captures the maximum remaining variance.
And it keeps doing this.
It keeps finding these orthogonal directions, each capturing progressively less of the remaining variance until you have as many new axes, principal components, as you had original features.
So it's like reorienting the data. Finding a new coordinate system where the most important patterns, the directions with the most variation, line up nicely with the first few axes.
That's a really good way to put it. It mathematically transforms your data into this new coordinate system where the new features, the principal components, are guaranteed to be uncorrelated, and they're ordered by how much variance they capture.
Which means?
Which means you can often just keep the first few principal components, the ones that capture, say, 95% of the total variance, and discard the rest. Those discarded ones mostly represent noise or less important variations.
And boom, you've reduced the dimensionality, potentially massively, while keeping most of the important information.
Precisely. You've cleaned it, compacted it. It simplifies the problem enormously for whatever learning algorithm you feed this transformed data into next. PCA is a smart, often essential pre-processing step before you get to the fancy AI learning engine part.
Okay, wow. We've taken a real deep dive today, covered a lot of ground. We started with those foundational ideas from Turing, the engineering perspective, the fields he basically predicted.
Search, reasoning, knowledge representation.
NLP, vision learning. Then we explored that big philosophical challenge from Searle in the Chinese room, making us really question what understanding even means for a machine.
Yeah, the difference between just following rules and actual comprehension.
And we got into the practical core of a lot of modern AI, this idea of function approximation and the absolutely crucial and often pretty messy reality of data.
The need for training data, testing data, the problems of too little or too much.
And ending with a key technique like PCA to try and make that data more manageable and useful.
It really highlights that AI isn't just about complex algorithms, is it? It involves these fundamental challenges in defining intelligence itself, grappling with the quality and quantity of data, and constantly asking whether our systems are truly learning concepts or just becoming incredibly good at mimicking behavior or memorizing patterns.
Thinking about that difference again between systems that follow rules flawlessly, like the Chinese room, or maybe even a super sophisticated lookup table, and systems that can truly understand or generalize from very little information, like humans seem capable of. Where do you think the biggest leap in AI needs to happen next? Is it just better algorithms, smarter data preparation, or is it something more fundamental, a different approach entirely?
That's definitely the question, isn't it? A lot to ponder there.
Absolutely. Keep asking questions, keep exploring, and keep diving deep.